this video, I'm just going to include all of the wave stuff to just get it all done in one video. So we started the year off with the waves basics. The waves basics included talking about period, which is the time for one cycle. So if I needed to find period, I would do the time divided by the number of cycles, vibrations, waves, whatever that is. Frequency is the opposite. It is the number of cycles in 1 second. So to find the frequency, I would take number of cycles divided by the time. You'll notice that these two are inverses of each other, so I can also find the period by taking the inverse of the frequency, and I can find frequency by taking the inverse of the period. We also talked about wave parts. So you need to make sure you're looking at what the axes are. So if this was a distance m, and this was a distance m, and m is for meters, and I drew my wave in here, this would not give me any information about the period or the frequency. What it would give me information on is the amplitude and the wavelength. Okay? Wavelength can also be measured as the distance from crest to crest. It's a crest plus a trough or trough to trough. If I had the same wave, but my graph had time in seconds on the x-axis, then now I can tell information about the period. This would still give me information about the amplitude, and I should probably put in the positive and negatives here. And then the zero position for this one is the equilibrium position. It doesn't always, the graph, it doesn't always have to start at zero though. This is still the amplitude. But now we would find the period from this, and the period is the time for one cycle. So that would be a period, or crest to crest would also be the period. Okay, so wavelength comes from the graph that has meters on the y-axis and meters on the x-axis. Period and frequency come from the graph that has meters on its y-axis and seconds on its x-axis. The other things we talked about with waves was velocity is wavelength divided by time. But velocity or wave speed can also be found by that was not wavelength divided by time. This was wavelength times frequency, or distance divided by time. The reason this works is because frequency is 1 over the period. Wavelength is equivalent to a distance. So if I did the wavelength times frequency, which is 1 over period, I actually get this equation. Okay, so you don't want to be a slave to the equations. You need to look at the information that you are given in the problem. Okay, the other one I get a lot of questions about is the amplitude of motion. If something tells you that a wave has a period of 2 seconds, that means in 2 seconds, I get 1 wavelength, okay? So this would be at my 2 seconds. Well, that means this was at 1 second. And please, this is not drawn to scale. I do my best, but it is what it is. That means at 3 seconds, I would be here, and it's going to keep on going. So this would be 4 seconds, 5 seconds, etc. Okay? Every time a wave moves, I go up the amplitude and then down the amplitude. So for every crest, the distance traveled is 2 times the amplitude. For every trough, the distance is 2 times the amplitude. So if they told you the period was 2 seconds, what is the amplitude of motion for 5 seconds? Well, the amplitude of motion for 5 seconds would be, well, this is going to be 2.5 wavelengths. In one wavelength, I get 1 crest plus 1 trough. So if this is 2.5 wavelengths, that means that this object would travel through the crest 3 times if my wave started like this one, because I would have 1 crest for 1 wavelength, the second crest for the second wavelength, and then the third crest here. So that'd be 6 times. Okay, so it's going to go through 6 crests. And then it's going to go through 1 trough, 2 troughs. So if every amplitude, the amplitude happens twice for a crest, that means this is 6 times the amplitude. 6 times 2 amplitudes, which is 12 amplitudes. So that went through the amplitude 12 times. 2 troughs would be 2 times the amplitude, which would be 4 times the amplitude. So for the example I gave you here, 16 times the amplitude is going to equal the distance traveled. So if they told you the distance was 160 meters, then the amplitude was 160 meters divided by 16, or 10 meters. That's how you get the amplitude of motion for that type of a wave problem. Okay, then I'm going to move on to law of reflection. Just really briefly on law of reflection. It's going to be off from a solid surface. You're going to have your light ray come in to the surface. You have to draw a normal, and a normal is perpendicular to the surface. You need that normal because this is your angle of incidence. Then the light ray is going to reflect off, and this becomes your reflected ray. Well, the angle of incidence has to equal the angle of reflection in the law of reflection. You need the normal because that's where we draw the angle in reference to the light ray. Okay. The law of refraction, or Snell's law, is what we use there. That's when light bends. So the law of reflection, this is reflecting light. Snell's law is bending light. And we refer to that bending light as refraction. So Snell's law says that the sine of angle 1 times the index of refraction of material 1 equals the index of refraction for material 2 times the angle, the refracted angle in material 2. So this is when you had like the glass block, like the lab we did, and the light came in here, and then the light was let me adjust my box. Okay. So the light would come in here, it would bend inside the material. So this would be material 1, this would be material 2. And then it's going to come out the other side. And then you had to find the angle of incidence, which is this angle right here. That would be angle 1. And then we're going to get this bending. And we again measure that angle. Oh, let me put an arrow on my ray there. And this becomes that angle 2, okay? Or incidence angle is what angle 1 is. Angle of refraction is angle 2, okay? If N1 is greater than N2, then the light bends away from the normal. If N1 is less than N2, the light bends towards the normal. If we wanted to measure the angle that the light left the material at over here, you would need another normal, and then this would become your refracted material, and this becomes your incidence angle. And this is going to be the same as angle 2 here, but it would then be considered angle 1 in our equation. And this angle 2 and this angle 1, those would be equal to each other because it's going back out into the same material it entered in. And then last but not least, we had the equation that ties together the speed in the new medium to the speed of light in a vacuum. And we said that the index of refraction would be equal to the speed of light in a vacuum divided by the speed of light in the new medium. Okay, so N is the index of refraction here. And C is the speed of light in a vacuum. And I can never spell vacuum right. I think it has 2 C's, right? And then V is the speed of light in the new medium. So if you were trying to find an index of refraction and you knew the speed of that light in the medium, then you would just use speed of light in a vacuum divided by the speed of light in the new medium, and then you could find the index of refraction. Okay, moving along, we talk next about the EM spectrum. And the biggest thing here is to know that as you go from, I don't know why I made a box, as you go from radio waves all the way over here to gamma waves, that as you go from here to here, the frequency increases and the wavelength decreases. And if you go from gamma rays over to radio waves, you have a decrease in frequency and an increase in wavelength, okay? The other thing you need to remember is that all EM waves move at the speed of light, which is about 3 times 10 to the 8th meters each second in a vacuum, okay? They all travel at the same wave speed. That's why you get this relationship here, because we still use wave speed is equal to frequency times wavelength, or wavelength times frequency. All right, the last thing I'm going to talk about is those standing waves and resonance. So standing waves on strings. So standing waves on strings. Strings have to be attached at both ends, so they have fixed ends. I meant to make a bigger wave, okay? So remember, for a standing wave, this is not necessarily that these are happening simultaneously, because I have one string, so the string can't be up and down at the same time. But the wave motion is happening so fast that to our eyes, it looks like this is one motion, okay? So this would be the first harmonic. And the first harmonic is where you get the fundamental frequency. That fundamental frequency is the lowest frequency this wave can have. You can also look at this as this is one antinode. So n equals 1. And this is going to be the equation where wavelength equals 2 times the length, because the length of this string, where L is the length of your string. Let me go ahead and add that here. And it takes 2 lengths of those strings because, as you can see here, we only have a crest or a trough. And a full wavelength is a crest plus a trough. But we can find this for any harmonic by taking 2L over N. So since these have to have fixed ends, you are always going to end at a node, and then you'll have an antinode. So the one I just drew here, I have 1, 2 antinodes. So this one is the second harmonic. And the wavelength for this one, since it's 2L over N, is just going to be equal to the length of the string, which is exactly what we see here. It's a crest plus a trough. To get the frequency of the second harmonic, it's just going to be, or any harmonic, is just going to be that harmonic number times the fundamental frequency, which is the one at the first harmonic. Standing waves on strings can have odd and even harmonics because I can draw a third harmonic here. And let me keep it the same width so you can see kind of how it looks. That is going to be a crest, a trough, and then back up to the crest. And I'm sorry I'm not drawing these to scale very well. I am doing my best, okay? This is the third harmonic because I have 1, 2, 3 antinodes. So I can find the frequency for this one by taking 3 times that fundamental frequency, or whatever the frequency of the first harmonic is, okay? You also have an equation on your equation chart that has the wave speed in it. And it's just a combination of this equation and the wave speed equation, which is still just wavelength times frequency, or frequency times wavelength. So this was for strings. So we can also have open-end air columns, or an open-end tube. And what we get in the tubes is something similar. For the first harmonic, we're going to get like half a crest and half a trough. And that's because these start and end with an antinode, okay? And then, again, our eye, if we could see these vibrating molecules, it would look like there were 2 waves happening at the same time, but it's not. It's the same wave going to the right and going back to the left. So this one I said was the fundamental frequency because I have 1 node. And so since I have 1 node, this is the first harmonic. And since I have half of a crest and half of a trough, the wavelength for this one is also going to be 2 times the length, where L is the length of the column. And then that's going to be divided by N, where the N is the harmonic. Which for these, again, will be how many nodes it has. So if I'm doing the second harmonic, I'm going to have half of a crest a full trough, and then another half of a crest. Okay, and then the same thing is going to be happening here. So you'll see I have 1, 2 nodes, and it's my second harmonic. The way the harmonic frequencies work is the exact same way that they worked before. I forgot my N in there. And it's the harmonic number times that fundamental frequency or the first harmonic. Also can get even and odd numbered harmonics here. So if I wanted a third harmonic, I'm going to get half of a crest, a full trough, half of a crest, and then half of a trough. Let me make my column a little longer because I overshot that a little bit. And then the same thing here. And now you can see I have 1, 2, 3 nodes. So this is the third harmonic. All right, last but not least are the closed end tubes. And for the closed end tubes, it's just like it sounds. It has a closed end. So for this one, it's going to start at a node and end at an antinode. So this has half of a crest or half of a trough. So this is where the 4 comes into play, because I'm going to need 4 lengths of this tube in order to get the full wavelength. So for these, your wavelength is equal to 4 times the length of the tube divided by or air column or whatever you want to call it, divided by the harmonic number. So this one is the first harmonic or the fundamental frequency. These, you can only get odd numbered harmonics. And that is because it has to start at a node and end at an antinode. So I would get a full crest and then half of a trough. And so this is the third harmonic. And the best way I can tell you to count these, or the way it makes sense in my mind, is you ignore that first node, but it has an antinode here, a node here, and then a third antinode here. And so that's how I count them. Or you could count all the nodes plus the antinodes and then subtract 1. That would work also. Everything else is the same, other than there is an equation on your equation chart that has this 4L in it. So keep that in mind. And then these can only have odd numbered harmonics. So, but you can still find the frequency for any harmonic by taking n times the fundamental frequency. But again, this can have the fundamental frequency, the third harmonic, the fifth harmonic, the seventh harmonic, etc. It cannot have even numbered harmonics because this type of tube cannot end on a node. I did post the answer key for the standing waves practice, and it has a lot of practice drawing these and calculating different pieces. So I highly suggest looking at that standing waves and resonance practice worksheet if you have not looked at that already. All right, I hope this helps. Good luck on the midterm.